Three spheres with radii 11, 13, and 19 are mutually externally tangent. A plane intersects the spheres in three congruent circles centered at A, B, and C respectively, and the centers of the spheres all lie on the same side of this plane. Suppose that AB squared is equal to 560. Find AC squared. Okay, so the first thing you might want to do when you see this problem is draw out a diagram of these three spheres, but you quickly realize that it is very difficult to try to draw a 3D diagram of three tangent spheres. It's going to look something like this, and it's going to be very hard to work with. So instead, what we're going to do is we're going to take what we know. We have a plane intersecting the spheres and it's going to intersect each sphere in such a way that the three intersection cross sections are congruent circles, and their centers are A, B, and C respectively. So if this is the sphere with radius 11, and you have this cross section, and its center is A, and it's going to have the same radius as the sphere with radius 13, and which has this cross section, and its center is B. These two circles are going to have the same radius. So instead of trying to draw out all three of the spheres at the same time, what we're just going to do is we're just going to draw out the first two, because we know a little bit about them. We have the distance between the two centers of that cross section is going to be the square root of 560. So what I'm going to do is I'm going to draw out one sphere and then the other sphere. And actually, instead of drawing out the entire sphere, I'm just going to draw the cross section that includes the centers A, B, and C. So imagine you have these two three-dimensional spheres, and then you take a plane and then you slice it kind of like this. And then you just take the cross section of these two spheres that includes both of these centers. So this is going to be point A. This is going to be point B. We're going to call this common radius R. And this length is R as well. And we're going to have these two centers of the two spheres. I'm going to call them O1 and O2. And I am just going to draw two radii, because we should remember that the radii of the two spheres are 11 and 13. We'll get to the third sphere eventually after we deal with these two. So, I'm going to claim that just based on what we have here, we are able to find this common radius of these three cross sections. So what I'm going to do is I am going to connect O1 and O2, and note that this segment should go through the point of tangency, just regardless of what it looks like in the diagram. The diagram is not accurate. This segment O1, O2 goes through the point of tangency, because if you draw this tangent, you have the radii are both perpendicular to this tangent, which means they must have a straight line over here. So O1, O2 goes through the tangency point. So this length is 11, this length is 13, and this entire segment has length 11 plus 13, which is 24. That's cool. What are we going to do next? We have AB squared is equal to 560, which means that AB is equal to the square root of 560. Square root of 560. But how's that going to help us? Well, one thing we can do here is we can use the fact that if you have a circle and you draw a chord, the center of the circle, if you draw a line to the midpoint of this chord, this comes down at a perpendicular angle. And you can prove that using congruent triangles if you want. I'm not going to do it here. So O1A is a right angle. O2B is a right angle. And I'm going to draw one more length, which is the perpendicular from O1 to O2B right over here. And because this angle is a right angle, and this angle is a right angle, and this angle is a right angle, these 4 points lie on a rectangle. And what does that mean? It just means that this length, this purple length over here is also equal to root 560 because opposite sides of a rectangle are equal. So that purple segment has length 560. And what we're going to do now is we're going to realize that, hey, we actually have 2 sides of a right triangle, this right triangle over here. So we can find the third side by using Pythagorean theorem. So we have this length over here, which I can call x squared plus this length squared, root 560 squared, which is just 560, is equal to 24 squared, which is 576. So x squared is equal to 16. So x is equal to 4. How is that going to help us find the radius? Well, recall that this was a rectangle. So how are we going to use that? Well, we use that because recall that the opposite sides of a rectangle are equal. So this green length is equal to this green length over here. And the green length is equal to, well, remember this is r and this is r. So the green length is equal to square root of 11 squared minus r squared from this right triangle over here. And so this length is equal to square root of 11 squared minus r squared as well. How's that going to help us? Because the green length plus 4 is equal to this brown length over here, BO2, the green length plus this 4 over here. So that is going to be equal to, well, you have a right triangle over here, right over here, and you have 2 legs, and you can find the third, and the third is actually equal to the green length plus 4, which is equal to, by Pythagorean theorem, 13 squared minus r squared. So now we have an equation for r, and we can actually solve for this common radius of the 3 cross sections. So what we do is we will square both sides of this. This left-hand side becomes square root of 11 squared, which is 121 minus r squared. This squared plus 4 squared plus 2 times 4 times root 121 minus r squared is equal to the right-hand side squared, which is 169 minus r squared. This thing over here becomes just root 121 minus r squared, and you can add r squared to both sides. You can also subtract 121 from both sides. This becomes a 48. You can subtract 16 from both sides. This becomes a 32. Divide both sides by 8, and this becomes a 4. You can square this. You get 121 minus r squared is equal to 16. R squared is equal to root 105. No, excuse me, r squared is equal to 105, which means that r itself is equal to root 105. So that's the common radius between all 3 of the circles. And we can use this radius to help us find AC using essentially the reverse of what we did here. So I am going to clear all of this except r is equal to root 105. And this time, what I'm going to do is I'm going to draw a different cross section. We have our r, and we want to find our AC squared. And how we're going to find our AC squared? Well, what I'm going to do is I'm going to say A is in sphere with radius 11, C is in the sphere with radius 19. I'm just going to draw those two. So this is the smaller sphere, and this is the larger sphere over here. And they're tangent here. And what we're going to do is we're going to kind of draw this where the plane would intersect it, and we're going to take the cross section that goes right through the middle of these two, so that this is the center of the circle and this is the center of the other circle, C. And now we're going to do essentially the same thing. We're going to call this center O1. This center over here is going to be O3. And we're going to draw O1, O3. And remember, by the same logic we had before, O1, O3 goes through this point of tangency, which means that its length is just the sum of the radii, 11 plus 19, or 30. And we'll construct our diagram in essentially the same way. We're going to draw O1A and O3C at right angles. And we're going to draw this perpendicular from O1 to CO3. And this time we have some information because this radius is root 105. And this radius is root 105 as well. And this length is 11. And this length over here is 19. So how are we ever going to find AC? Well, we can use the fact that AC is equal to this length over here. And I'll do it in a different color. I'll do it in this orange color over here. You just need to find the length of this orange segment, which is equal to AC because you have a rectangle over here and the opposite sides are equal. So you just have to find this orange angle, and that's what AC is. And that's great because now we're on the right track. So what do we do? First of all, we can find AO1, which is by Pythagorean theorem, square root of 11 squared minus root 105 squared, which is equal to root 121 minus 105, which is equal to root 16, which is equal to 4. So this length has length 4. So this length over here also has length 4 because, once again, O1, AC, and this fourth point form a rectangle. And furthermore, you can also find CO3 by looking at this right triangle. Hypotenuse is 19, leg is root 105, so CO3 squared is equal to 19 squared minus root 105 squared, which is equal to 361 minus 105, which is equal to 256. Take the square root of both sides. CO3 is equal to 16. Which means that this length over here, which I'm going to do in yellow, is equal to 16 minus 4 is equal to 12. Okay, now we're almost at the end because we have a way to find this orange segment. We take this right triangle, which I'm going to highlight in blue. This right triangle has hypotenuse 30. Leg length 12. So the orange segment, orange, is equal to square root of 30 squared minus 12 squared, which is equal to square root of 900 minus 144, which is equal to square root of 756. So AC squared is equal to root 756 squared, which is equal to 756. And we are done. Thanks for watching, and I will see you next time.